Hi, welcome to the 11th class session of quantitative topology 2 and video course. Shall we? I'm currently doing a research and functioning at my address. So, in that going through, so today we shall first with the assignment problem. We name the victim assignment and then we'll solve objective, subjective both. Okay, and also I have checked the practice assignment in the website for the week 10. So I think it's better to go with also the practice assignment solution discussion. Okay. So let's start. So first question is let x comma less than equal to the linear order set where x is a finite set. Then on x is the discrete topology. The true or false question. Okay. As follows. Okay, so the question is as follows: x comma less the x is a set with order relation less than equal to, and x is given to finite set. Now, with respect to this order, we are giving the order topology on capital X. Now, the question is that the order topology in capital X is a discrete topology. It is a true or false. Okay, that's what we need to understand. So, how to tackle this problem? Well, first of all, okay, let's start with examples. So, let x equal to x1, x2, x3. Okay, we're actually that's an order relation. So, x1 less than x2 less than x3. Okay, I mean everything is considered increasing order. Okay, now what we need to check? It is showing that it's discrete topology. That means to say what? We need to show every set is open. That is similar to saying that every singleton is open. We need to check, right? So how what to do? So first of all, x1 is the least element. So x third bracket x1 for open x2. This contains all those x that x1 less than equal to x less than x2, and this contains strictly s1 only. So x1 is open. Similarly, open set x1 x2 sorry open set x1 x3 is equal to singleton x2. So singleton x is also open, and open set x2 third bracket x3, this is on the singleton x3. So these employers, so each point x1, x2, x3 are open in X. So this means that it is a discrete topology. Okay. Well, this is an example we have started with. Now let's try to generalize. So basically, what we need to do, we need to show that each point is open. Right now, in this our example x1, x2, x3 point length. Uh, the least, the smallest element can be found out as third bracket close x1 comma open x2. The other elements can be found out like open interval some two elements as alternates of left side or one alternate right side, and the extreme large element, the largest element can be found out at x2 comma x2 third bracket. So if we use this method for arbitrary set, now let x be the set x1, x2, x3, xn minus 1, xn, and we can assume without loss of generality, assume that x1 less than x2 less than x3 or less than xn, then singleton x1 is equal to third bracket x1 from x2, singleton xn is equal to open xn minus 1 third bracket xn, all the singleton xi is equal to open xi minus 1 xi plus 1, xi belongs to x2 dot 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 x. So this is what? Each xi is open. This is what? Topology. So this is topology of x squared. You understand? So this is that's why you can show there is a discrete topology. So normally mental basic technique is to we need to understand how we can get each singleton set in form of open set of the our topology. I mean, especially the phase element or topology. That's all. Okay. So there is a solution for the first problem. Now let's go to the second one. What is the question? Question is here x is continuous edge from close 0 1 to close 0. How to tackle this problem? So look, in order to access some kind of existence in topological space, there are some basic things like compactness, like connectedness. Okay. Now observe that both sides are compact. This closed boundary is compact. Okay, so compactness will not work. I mean, in order to give some kind of contract travel. But consider connectedness. Closed 0, 1 is a connected, but closed 0 open omega it is not connected. Okay, and if such a continuous map exists, this implies what? This implies f of 0 1 will be connected. But if it is onto the f of third bracket 0 1 is equal to third bracket 0 3, so it's a contradiction. Okay, so that's why There does not exist a continuous onto map from close 01 to close 0 close omega. Okay. So here we only need to use topological properties in the connecting, and that suffices the problem solved. Okay. So there it's a false argument. Understand? Okay. I want to do one thing. While going through the videos, if you have any doubt or any problem understanding, you can email me. I will reply. Or you can comment over the YouTube video. I'll reply. Okay. But make sure kindly try to make honesty of this live session, because these sessions are actually for your. I mean, this session in this session actually we are trying to make your concept much clearer, much more. Okay, so try to make use honest use of these live sessions. Okay, so let's go to the third problem. Third problem is close 0 comma omega is factorized. It is true or false? So question is close 0.3 metrizable is true or false? How to tackle this? Okay, so first of all, well, I mean, since this is an abstract space, so it is not, there is no kind of visualization we want. Okay, so in order to solve this type of situation problems, you need to try to always use some kind of property in order to get some contribution. So, for example, we know the metrizable space is normal. We know metrizable space for countable. Okay, so try to think that whether this property has, I mean, closed zero infinity has the property which contradicts the connect countability or the normality. So in this way, we can attack this type of problems of abstract spaces. So of course, you might have seen, I mean, in source note, it's clear that closed zero infinity, I mean omega, has no countable basis at, I mean, closed zero infinity has no countable basis at omega. So this implies what? Closed zero infinity, not first count. It is not a first countable space. So closed zero comma omega is not metrizable. So let me repeat how to attack this problem. So first of all, observe that any metrical space is normal and it's countable. Okay. So now closed zero point infinity is, I mean, it does not admit any counter. They exist at omega. So closed zero comma omega is not first countable. So closed zero comma omega is not a metrical space. Okay. So this is the contradiction. That's a closed zero comma infinity is not metrical. So the answer is false here. Okay. So this is the argument. I mean, in this way we can. I mean, in this way we can have this kind of problem because it's kind of abstract space. Okay. So let's move on to the next problem here. Here it's long or either true or false. So the question is, there exists embedding from a long ray to Earth. So I hope you all know. I mean, you all remember the definition of long ray. If you can't remember the definition of long ray, first go with the definition, then try to solve this problem. I mean, without definition, it's not possible actually. So the question is, that is embedding means what? It is a continuous injection. That is, I mean, that is, it is homomorphic onto its image. Okay. So I mean, there are many properties, but one property that is well and that is quite familiar, namely long range is not second countable. So if there exists an embedding theta from long ray to R, then this is the embedding. So long ray is equal to theta of L, and which is subset of R. Okay. Now R is second countable, real line is second countable, of course with usual topology. And since subspace of second countable is second countable, so theta is second countable, tells the long line or long ray is second countable, and that is the contradiction. So there does not exist any embedding a long ray to R. Okay. So let me repeat the argument. Okay, so as I have mentioned already, or as we have seen in the previous problem also, in order to attack this type of abstract problem, first we need to remember all the properties of the particular space. Okay. Now, long ray have many properties, but of course there is one property everybody will know, that is long ray is not a second countable space. Okay. So if there is an embedding theta from long ray to R, embedding means it is homeomorphism onto its image. Then L is homeomorphic to theta L, and Since R is second countable and south second countable is second countable, so theta of the long ray is second countable. So this is long ray second countable. So it's a contradiction of uh yeah, kindly wait as well. Hello, hello, hello. Okay, hello, okay. কে এটা বুঝলাম না। Okay, yes. Yeah. So, oh, so basically, yeah. So as I mentioned, we have the second counter property is making some contradiction that if long ray has an embedding inside real line, the long ray has the same model, but it's not from the property. So that's why there does not exist any embedding from long ray to us. So one second. Yes. Hello. 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 Yeah. So there is a contradiction. So that is there does not exist any embedding from long ray to earth. Okay. So it's a contradiction. So that's why the answer is false. Okay. Now the question is that there is a proper continuous method, yeah, from closed zero open. Now question is how to tackle this problem. Okay, so the problem, I mean, so what is the proper map? Proper map means P inverse single nova is compact for each nova. That is proper map means inverse image of each singleton is compact. So this is what I mean the proper map. Okay, now the question is, does the proper continuous map close it open omega to real line? Okay. So how to solve this problem? So let's try to think about what are the properties does we have closed zero open omega. Is there any property like any subset which is open, any subset closed, or any kind of thing like any set is open, you can only something like this, something like is there any type of property? Try to think about. Okay, so how to solve this problem? So first of all, also that first if has will be constant, if will be an if will be constant. Okay, means how? So likewise we have seen that from RL to RL to world level topology or any map is constant, any constant constant, right? The same around work here. So any map close to minimal real line is not, it is not constant, it is a eventually constant. Okay, that is there is some x in the space such that f of third bracket x omega is equal to singleton r, and then clearly f inverse singleton r contains third bracket x open omega, and hence so it is unbounded, of course, and so cannot be compared. Okay, so this is the argument. So 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 the thing is, here the property we have used that any continuous map f close zero open omega to real line is essentially constant. Now you might think why this is, it is not very difficult. Just think about it. What is omega by definition? go along definition, you will get the answer why integral is eventually constant. Okay? So this means what we can get excel that if third x open anywhere is smaller. So if inverse smaller contains closed x open omega, so it is unbounded and so it cannot be constant. Okay, that's all. So the answer for this question is false here. Okay. Now there is the last question in this which hunt the longest line. Sorry, where is the pen? So, the longest line L is first countable. Now question is how. So first it is true or false. The longest line is first one. Think about it. So the thing is, first one is what we need to check. So every point there is a countable basis at every point. Okay? But by definition, by its properties, what is the longest line? So longest line is something which every says that every point is open neighborhood homeomorphic an open interval of R and real line is first countable. So it is the first countable space. So every point of L has a neighborhood homeomorphic with an open interval of R and R is first countable. So any point of L has a countable basis. So this is the argument. Kindly wait for a moment. So yeah, that is the argument. Okay. So it's not true. Okay. So now let's go with some other parts. Okay, let me divide this. Oh, so let's move the subject to a simpler. So first question is um, give an example of a linearly ordered set. That is fine. The property that between any two points, where is this, and such that the space is not okay. So how to tackle this problem? So what is the question? Give an example of a linear order set X from adjacent satisfying the property that between any two distinct points there exists another point that should have such that space is not connected. So we know well that linear continuum is connected, but there are two properties. This is one property, another property is LU property, right? So we need to give an example which has this property but not LU property. So as this has been is this basic example we know from the real analysis. So what is the obvious space? What is the obvious subset of real line which does not have an LU property? R. So Q. This Q has this property mentioned above, but it does not have an LU property. So anyway, this okay. So this is the answer. I mean, yeah, it's the obvious. It's kind of easy answer, but it's a quite tricky problem. So let's go with the next problem. So the next problem is the following. Let me get it. So next problem is the following. So that the set A of elements of 0, omega, which are not immediate successors given. The set A of elements closed to open omega, which are not immediate successor is under means what? What does the immediate successor? What? Suppose suppose S is an element which is an immediate successor means there does not exist any S dash between this. Okay. After omega we can directly go to S. There is nothing in between. So it's not an immediate successor. Okay. So okay. So think about it. How to tackle this problem. I shall be back after some minutes. So, okay, so the way of this type of solve problem, in order to solve this, the one usual method is to go the method of contradiction. Okay, so how what to do? So let be counter. Okay. So you know what? Supremum exist. Okay. Then S is equal to. So supremum exists. So call it the smallest. By the way, I'm following the same notation as given answer. So there should not be any notation problem. Okay. So wait. So call it smallest. So now we are going to start inductor process. Put A is equal to S0. S1 is equal to S0 plus 1 dot 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 Sn is equal to Sn minus 1 plus 1. And this is an immediate successor of Sn minus 1. Okay. Then Sn will converge to a point t belongs to third bracket close 0 open omega, which is a supremum, so which is nothing but supremum of the set Sn, because we are using it in increasing. Okay. And so, and let T where T is the limit of S. Okay. So this implies what? This implies T is not an immediate successor. Okay. So this implies what? So, but observe that T is not in a with a contradiction. So let me give the argument. Right. So what is the full argument? Full argument is following. So suppose we have used the method of contradiction, and suppose that sorry, yeah, suppose that yeah, suppose that capital A is countable set, so supremum exists. Okay, so I will call this supremum S to small s. Now we are going with the method of contradiction. So now we are going to make some inductive process. So first we are putting small s not to be small s. S1 is equal to small s not plus 1. And order Sn is equal to small sn plus 1. Okay. So and where small sn is nothing but the immediate successor of Sn minus 1. Okay. Now the A is equal to so, so then Sn small sn will converge to a point P belongs to third bracket 0 open omega, and which is supremum S. So the supremum Sn is not then, of course, because the sequence Sn is strictly increasing because each next term is immediate successor of just a previous term, and T is equal to limit S and T is not an immediate successor. But P does not also belong to capital S, so it's a contradiction. Okay. So this is the argument. So that's what the problem is. So now let's get the following problem. So it's an example type problem. Give well-ordered relations less than equal to 1 on or at 1/3 of n such that n less than equal to 1 and less than equal to 2 on not of same type. So we need to find example of two orders with order relation is equal to on the natural numbers. So those two are not same type. Okay. Same type means this. So R1 less than equal to R2. You can only f of R1 less than equal to R2. If this way is not, that is the same type. Okay. The possible way, one way is the following. And there may be many more ways, but as done in the SR, I am also going this direction. So first take this to the usual order n, this and less than equal to, and define less than equal to on 2, 3 dot the usual order, and n belongs to n, put n less than 2, 1. Okay. So this is for 1. So this is the usual way, and this is all n less than equal to 1. Now if possible, let they are of same type. Then here exists a bijection f from n less than equal to 1, which is order preserving. Okay. And let k belong further to n such that k less than 1 plus 1. Now f of k plus 1 less than 2 is equal to 1. So this tells that so f is not rectified. Okay, you understand? So, so what is the argument? So let me the argument here. So less than equal to is the usual order when and less than equal to 1, 2, 3 is the usual order and less than equal to 1. So this is the order 2. I mean this is the sorry. This is the non-obvious order. This is not the obvious order. Okay. So now we're assuming that there are 10 types. So this means what? There is a bijection F which is the order 2 third. Okay. So now since K and so the F of K equal to 1. So now if K less than 1, K plus 1, but if of K plus 1 less than 1. So if it's not also this is a contradiction. Okay. So that's why the chosen orders are not of same order type. Okay. So this is the argument. Well, first of all, this type of problem is it is not actually difficult to solve this problem, but it is actually quite tricky problem. Okay, now in order to solve this problem, you need to actually really practice these things each and every day, so that you can get some intuition how to approach this problem. And in reality, there is, I mean, I mean to say, there is no well-established method in order to solve this problem. I mean, these are just an intuition only for how that is solved. Okay. Sorry. Not okay. So, let's go to the next problem. Namely, so let's go to the next problem number 4. The problem is the following. Let x comma less than equal to be a linear order such that every counter subset of x with restriction of less than equal to is going on. Okay. Show that x is also well ordered. So for the problem that x was less than equal to the linear ordered set, so that every counter subset of x is a restriction of less than equal to the well ordered. Now we need to show that x comma less than equal to the well ordered set. Then we need to check that even infinite set as a low. Okay. So same here like previous problem, like the previous one, this problem also. There's one possible way to attack this problem, namely method convolution. So assume that if possible, X is not equal. So now well ordered. Then there will exist a non-negative A of X does not have increment. Now let A0 belongs to A. So this is like what? So there exists A1, A that A1 less. And if we go on, we'll find An belongs to A such that An less than An minus. So then the set B is equal to An, N belongs to N, is output. Set of X such that B less than equal to is not well. It's a contradiction. Okay. Sorry, it's not well ordered. Sorry. So the solution goes with the contradictory method. So first we have to assume that X is not a well ordered set. Then there is not a subset of X, so it does not have increment. Okay. So let A0 belongs to A. Then so there is this A1 belongs to A, so that A1 is less than N because it doesn't enter. So by following this process for each n, we will have an An belongs to A, so the N less than An minus. Then capital B is equal to N. So the countable subset of X such that B less comma less than equal is not a well ordered set. Okay. So it's a contradiction. So that's why X is a well ordered set. Yeah, so that's the full argument. Okay, that's the full argument. Well, okay, so kindly let us back to our sentence. Okay. So okay, so I think it's always better to go to revision first. So let's first revise what we have done today, and let's revise the institute and draft questions. Okay. So the first question is the following: that let x comma less than equal to be a linear order set for x mod x less than equal to fine. I mean, order x is a x has finite. Then the order topology on this is a discrete topology. Is it true or false? So that is the question. So you can remember how to approach this problem. First, we have started with some capital small x, which number of elements 3. x1, x2, x3. Okay. So now observe that this x1. What is the pen here? So now observe that the singleton x, the set singleton x can be thought as a base element of the order topology. Similarly, singleton x2 is a base on order. Similarly, single x is a base on order topology. Okay, so that's why points x1, x2, x3 are open in x. Okay, so it's a discrete topology. Okay, so this is for the three element set. Now we are going to do this for uh, infinite element for random finite number of sets. Okay. So for that, what we'll do once again. So, oh, so let x equal x. So now we are taking x to an arbitrary set. X1, x2, x2 dot we are taking. Okay. Now, so now you're taking arbitrary x for the points are x1, x2, or x7. Okay. We're taking small x1 is equal to x1, x2. So that is this steps was showing that any single element can be called as a basis element of the order to follow. This is what is because each xi belongs to the x2 x x. So each xi is an open in its topology of a system. Okay. So that's the each x open, so each set is open. So that's the argument. Okay. Now second question was that there is a continuous onto map from R to close 01 to close 0 infinity such that is a continuous continuous onto map from close 01 to close 0 close omega. Now, uh, now in order to tackle this type of problems, as we have mentioned earlier, that for that we need to do some kind of properties of this, like compactness, and we need to do kinds of properties. Now, thing is close 0 close omega is not connected space, but close 0 close 1 is connected space. So if this continuous map, then onto map exists, and then close 0 close omega must be connected, but this is not the case. So there does not exist any continuous onto map F from close 0 1 to close 0 omega. So that's false. Yeah. Okay. That's all it is. So now the next question is that close 0 close omega is metrizable. And that's this problem. So So now the next problem is the following: the closed zero closed loop is metrizable or not? Okay, it is a true or false question. So so metrizable, we know the metrizable space is normal, metrizable same countable. Okay, so for that we need to, for this problem we need to countable argument. That is closed zero closed omega is not first countable space because at the point omega there does not exist a countable local basis. Okay, so that's a closed zero closed omega is not the first countable space. But any metrizable is a first countable, so that's the contradiction. Okay, so that's why closed zero closed omega is not a metrizable space. It is not first countable. That is the main thing. Okay. So next problem. The, does there exist an embedding for long ray to R? Well, the thing is that first of all, the definition of long ray is quite tricky. So if you could not remember the definition of long ray, first go to the definition, then do the solution. Okay. Solution is as follows. So suppose long ray is not the same count. Okay. So there was the embedding theta from long ray to R. Okay. And it's subset of R. And R is sigma. Since alpha second countable is second countable, so theta L is second countable and L is second countable. So the main thing is that since if there is embedding, so L can inject inside real line. So that means we must have a surface of R which is homoerotic, long line. Okay, long. No R is second countable, so any surface is second countable. So the homoerotic copy of long ray inside R is second countable. And being a homoerotic copy, long ray is also same countable. So there is a contradiction, but long ray is not a same countable space. Okay. So that's why there does not exist embedding from a long ray to real line. Okay. Fifth question is that there exists a proper continuous map air from closed zero open omega to real line. So first of all, what does it mean proper map? Proper map means inverse image of singleton is compact. Okay. This is what I mean proper. Yeah. So first of all, since the map is close zero from open omega to real line, this map A is eventually constant when being continuous. Now, this property is not too much obvious, but if you go along the definitions of these things, then you will realize that it's eventually constant. Okay? So this eventually constant is what generates some x so that if of third bracket x comma open omega is a singleton r. Using the if in the singleton r contains third bracket open omega and it's just which is unbounded. So it cannot be compact, right? So I mean so this is the answer. Okay, do you understand? Oh, kindly wait for me. Oh, so if you must consider it's kind of a so there's a contradiction of perfectness of this map. Perfect map. Proper map. So that's why you are. So now the second last question was that the longest line L is first boundary. So it's true or false? So I'll do it. So I mean by definition of longest line is what? Longest line is nothing but has a neighborhood homogeneous an open interval. And R is first boundary. So any neighborhood of longest line is homogeneous with the open interval of R and R is first boundary to any point of longest line has a countable basis. That's the longest line is first boundary. Okay. So that's all for the MCQ type question. Now let's go to the study data question. So, So, so what are the first problem? First problem, give an example of a linearly ordered set x comma less than, order relation doesn't satisfy the property that between any two distinct points there exists another point, but does that the space is not connected. So, what is the answer? Thing is that we all know the concept of linear continuum. Linear continuum is a linear ordered set which has LU property along with this given known property. So if we we need to find a space which is not connected, so at least we need to find some space which is not connected, which has no LU properties. So the set of Q, the rational number has no LU property, and anyway it is disconnected. The Q has no LU property. This is only required in order to understand the example we may work on. Okay, that's all it is. There is no, that's all. That's the only included LU property. Okay. So next, show that the set A, the elements close 0, open omega, of which are not immediate subsets are an uncountable set. So first of all, what is immediate subset means? If it can take a S, then there does not exist any S prime so that this relation is immediate subset. But in between there is nothing. That means immediate success. Okay. What's so let A be countable set. Okay. We are going by the contradiction. So let assume A is a countable. Suprema exists, call it small s. So let A is equal to x. So let A so S1 is equal to S0 plus 1. So the usual approach is the what? So by method of contradiction. So let S suprema exist, call it S and put S equal to S. So S1 is equal to S1 plus 1, Sn equal to Sn minus 1 plus 1. Okay. Then Sn will converge to a point. Call it small t. Small t limit S. So T is not an immediate successor, but T does not belong to a contradiction. Okay. So that's all. Understand? Oh. So let's go to the next problem. The next problem is the following. So give two Euler relations less than equal to 1 less than equal to 1 as well, so that this and these are not of the same type, it's an order type. Means what there does, there does not the bijection fills up the order. Okay? So the same way we are going to construct two different order relations on natural number. One is less than equal to, which is an usual order of n, another is less than equal to 2, which is usual order, on the set 2 3 order, and putting small n less than equal to 1. Okay. Now, if possible, so we have two relations. This is less than equal to 1, this is less than equal to 2. So now, if possible, they are of same order. Then there is bijection f n comma less than equal to 1, n comma less than equal to 2, which is order preserving. Okay. This is order preserving, and now the bijections where k belongs to it, so therefore k equal to 1. Now k less than equal to 1 is the order relation 1. And but f of k plus 1 less than 2 x equal to 1, so f is not order preserved. So there is a contradiction. Okay. So there does not exist anything like it. That's all. So the next problem is the following. Okay. Okay. So yeah, this problem is quite a bit touchy. Okay. So now the next problem is that let x comma let x comma less than equal to be a linear order set so that every countable. So do note the condition. Every countable subset of x with the restriction of this is well ordered. Okay. So now we need to show that x comma less than equal to the well ordered set. Okay. So what we can do, the tools we have to attack this problem. So the way is method of contradiction. So if possible, let x is not a well ordered set, then there is a non-empty subset A of x which does not have influence. Let A not belongs to A and A1 belongs to A such that A1 less than H. Okay. Since it does not have influence, so we are getting n such that n less than n minus 1. B is equal to n, which is a countable subset x. So then b comma less than equal to is not a well ordered set. So x is a well ordered set. That's all. Okay. So we assume that there is not a subset A which does not have influence. So it doesn't have influence. So we are getting a sequence, decreasing sequence. Now the collection A is a countable set, and but we have assumed that not influence. So B comma less than equal is not a well ordered set. So with the contradiction, so our by answer wrong. That's the x well ordered set. Okay. So that's it. So basically, in today's MCQ and this survey questions, the main thing you need to understand is the following. You need to understand there are some whether some property, I mean, so metrizability implies countability, metrization is normality. So metrization is first countable. Those things you remember. There are some long line, long range. Those look, the long range there are many uh, properties, but in reality you need to keep in mind that long line is not a first countable, but it is second countable. This type of thing you always need to remember because this type of thing are actually helpful to solve problems. Okay, and also you need to remember one thing: the longest line, that it is something that each point has a neighborhood homeomorphic to the neighborhood of R. Okay, so this is something which seems quite useful in order to become counteractable or in solving problems. So this is a thing you need to remember. And in subjective question, most of the problem can be solved by using method of contradiction. Well, there's something, well, I mean, this problem can be solved by other ways, but in contradictory method actually is sometimes quite helpful. And I mean, I'm not saying this is always helpful, but in this situation, this is helpful. That's all. Okay, this may be solved in some other ways also. Okay. Now that problem close zero, close omega is metrizable or not. This problem is nothing but just observing the fact that this is first found or not. Okay, so do remember these properties for the final exam. So because that's will be actually is okay. Okay, so that's all it is. So let's move into some more problems because there are some minutes left. So there is something practice assignment, right? So let's dive into this. So there is one interest problem actually. So let me write the problem first. So let xi comma is equal to I equal to 1 comma 2 be two locally ordered sets, and if the order is in direction that the fifth order topology. So the question was the following: if xi and xi are two totally ordered spaces, it is not local, it's totally ordered spaces. And if x less than equal to 1 and y less than equal to dash be an order preserving bijection, then we need to show that if something ordered by bijection, the corresponding topological space which arose from the order bijection are the homeomorphism. So how to do? The thing is obvious. F of AB is nothing but FAB. So if A open will be open, then F of AB is also open, which is obvious by definition of order preserving maps. Okay. So I mean, so basically we need to understand one thing: F of open AB is equal to F comma. So that's all. It is something like continuous injective map is open. So that's also order preserving. It is strictly increasing map is order preserving obviously. So that is the open map. So in this case, it is the same thing. So yeah. So that's all it is. Okay. So okay. So let's end here. If you have any doubt or any question, you can ask me in the next live session, or if you have any email, I will reply. Okay. Thanks. I am doing the call.